Thank you, all of you, for joining us today for our Minerals on Mars webinar. We're so very excited because we have a fabulous speaker, Liz Rampe, and we are all, by the way, from the Astromaterials Research and Exploration Science, or ARES division at NASA's Johnson Space Center. So welcoming Liz, our speaker, who's so busy, but has found the time to be able to share Minerals on Mars with us. We thank you for that, Liz. We also have our facilitators, myself. My name is Paige Graff. I'm the lead facilitator for today, but I couldn't do this without our other facilitators or panelists, Rosina Miller and Sarah Simpson. They are both on the line to be able to respond to any problems you may be having, or to also help answer questions in that Q&A area if you are on the line with us live today. Now, I also want to welcome all of our participants, because we have participants from 42 states, Washington, D.C., Puerto Rico, and 31 different countries. What does that look like on the map? This is our map. So you can see we've got many of you from all across the United States, but really all across the world. And we welcome each and every one of you to this session today. We're so thrilled to have you, whether you're with us for this live presentation or whether you're listening to the archive. We've got a special treat for you today as we have Liz, be able to talk about Minerals on Mars. So my brief little introduction is just really a welcome to each and every one of you. And without further ado, I'm going to stop sharing my screen so that I can turn things over to Liz to share with all of us her information about herself and Minerals on Mars. So Liz, let me toss you the ball and make you the presenter. And
thank you.
Thank you for being here, Liz. Over to you.
All right. Thanks, Paige. Let me share my slides and put it in presenter mode. Let me find all of my stuff. Get set up. Yeah, thank you so much for that introduction, Paige, and thank you for facilitating this event, and thanks also to Rosina and Sarah for facilitating. So I am Liz Rampe. I'm a planetary scientist here at the NASA Johnson Space Center, and I want to start by telling you just a little bit about myself, and so you get a feeling of who I am and why I'm a planetary scientist. So I grew up in Colorado, just outside of Denver. Both of my parents are scientists. My mom is an archaeologist and my dad is a biologist. And so we spent a lot of time in the outdoors when I was growing up. And so here is a few photos of my sister and me camping and hiking in the Rocky Mountains. And so I developed a love of the natural world very early in my life. I also developed a love of dinosaurs, and so we spent a lot of time at the Denver Museum of Nature and Science looking at these beautiful fossils. And one of my very favorite places in the world is a place called Dinosaur Ridge, which is just southwest of Denver in the foothills of the Rocky Mountains. And here you can see hundreds of preserved or fossilized dinosaur footprints from where dinosaurs were walking along a shallow seaway in the interior of the United States in the late Jurassic, early Cretaceous period. And I was just so enthralled by the idea of being able to see evidence of these creatures that were on the Earth 100, 200 million years ago in these fossils. And so from an early age, I wanted to be a paleontologist and study dinosaurs. But, growing up, you sort of realize what's a practical job and what isn't. And so there aren't a lot of paleontologists out there. There aren't a lot of paleontology jobs out there either. And so I decided a more practical science to pursue would be chemistry. And so this is when I got to college. When I went to college in upstate New York at Colgate University, I decided that my major was going to be chemistry. But then I took an intro to chemistry class, and I didn't love it, and that really bothered me because I wanted to do something that I really loved. Luckily, my freshman year at Colgate, I also took a dinosaur evolution class, and that class took me right back to being a kid at the Denver Museum of Nature and Science, back to Dinosaur Ridge, and it really reinforced my love of dinosaurs. So I started to have this little voice in my head say, hey, you could be a paleontologist. But really the larger voice was like, no, that's not very practical. And so I left my decision of what to do sort of to the universe. In the final project for my dinosaur evolution course, it was a debate on whether to bring dinosaurs back to life, sort of like, Jurassic Park style. And so as part of this debate, you had to play a specific role. So you could be like a geneticist or a lawyer or, like a concerned citizen who doesn't want to be eaten by dinosaurs. But you could also be a paleontologist. And so to get your role, you had to pick a little, name folded piece of paper out of a fishbowl. And so I said in my head to the universe, I said, okay, well, if I pick paleontologist out of that fishbowl, this is just you telling me that that's what I'm meant to do. And so in this big lecture hall, we all had to go up on the stage and pick our role out of the fishbowl. And it was almost like, a Harry Potter style and the sorting hat. And it felt like this beam of light was coming down onto this fishbowl. I picked my little piece of paper, I unfolded it, and it said paleontologist. And I just breathed the sigh of relief because I knew that that's what I wanted to do. So after that class, I went to the registrar's office and I changed my major from chemistry to geology, and I really never looked back. But really what it taught me is that I should follow my gut and what I wanted to do, because I always knew that this is what I loved. And of course, in geology, there are more classes than just paleontology, and so I took other courses like mineralogy and learned that minerals are just as cool, if not cooler, than dinosaurs. So I got to do some undergraduate research where I was studying the clay mineralogy of some soils in the Adirondacks using X-ray diffraction and X-ray fluorescence spectroscopy, and this is really cool looking back on it because those are the same minerals and same techniques that I study on Mars. So from undergraduate school, I knew I wanted to get a PhD. I sort of cast this wide net with a bunch of applications, and my soon-to-be advisor at Arizona State University saw my application and saw that I studied clay minerals on Earth and said, do you know that there are clay minerals on Mars, and do you want to study them? And I had no idea about Mars, but I thought it sounded really cool. And so as part of in my PhD, I learned all about minerals on Mars, studied them, and from there came here to JSC to do a postdoc, and was eventually hired as a scientist. And so that's a little bit about how I got to be where I am. And then just to tell you a little bit about what I do here at NASA, I work on the Mars Science Laboratory Curiosity rover. I will tell you more about that. But I also do other research. I do a lot of analog work. So work to prepare for future robotic and crewed or human missions to the moon and Mars, and research out in the field to better understand the results that we're getting back from Curiosity and other missions to Mars. And so at the bottom here, I'm doing some analog research in cold and wet environments. This is what we think Mars was like maybe 3 or 4 billion years ago. And so here I am in the in Three Sisters in Oregon, outside of Bend, and here I am in Iceland, actually doing X-ray diffraction in the field. This is an X-ray diffractometer here, very similar to the CheMin instrument on Curiosity. And then I also do some robotic analog missions where we have taken rovers and instruments to locations that are similar to the Moon and Mars. So this again is in Iceland, testing different instruments and operational scenarios. And then I've participated in human analog missions and in some cases have been a crew member. Okay, so that's what I do at NASA. Today, we're going to talk a lot about minerals. We'll talk about why minerals are important for understanding really any planet's geologic history. Talk about the minerals that have been found on Mars and what they tell us about what Mars was like in the past. And we'll go into detail about what we've found in Gale crater with the CheMin instrument on Curiosity. And I'll end with just a few closing remarks on future directions of planetary mineralogy. So starting just from a basic level, a mineral is a naturally occurring crystalline solid with a definite but not necessarily fixed chemical composition. Let's break down that definition. So naturally occurring means minerals are not man-made, human-made. They are made by nature. Crystalline means that the atoms in a mineral are in this regular repeating order structure, or what's called a crystal lattice. And definite but not fixed chemical composition just means that minerals are made up of a specific combination of elements, but some elements can substitute for one another in the structure. The atomic structure and elemental composition of minerals control physical properties like color, crystal habit, or how the crystal grows, and hardness. And this photo on the right is just a collection of different minerals showing off the range of color and crystal habit or form. Beautiful. Minerals are an important key to understanding a planet's geologic history. They precipitate from physical, chemical, and biological processes, at least in the case of Earth. And what's really important about minerals is that many of them form under specific conditions. And so when we find certain minerals in a rock, it can tell us a lot about that rock's history. For example, igneous minerals can tell us about magma or lava composition and its evolution. Metamorphic minerals tell us about the pressure and temperature conditions that that rock experienced. And minerals in sedimentary rocks can tell us about the types of rocks that those sediments eroded from, the surface environments in which those sediments were transported and deposited, and how those sediments lithified or became a rock. Okay, so Paige let you know that I was going to ask you some questions just to engage with you. The first question for you is, how many types of minerals have been identified on Earth? Is it A, 60, B, 600 minerals, C, 6,000 minerals, or D, 6 million minerals?
All
so
right.
I encourage you to put your, yep, go ahead, Paige, sorry.
Yes, thank you for encouraging them because we're getting in a lot of answers. I'm seeing a whole slew of C's. We're getting a couple of 6 million, so the letter D. We're getting one group from one of our high schools is thinking maybe D. A few folks, a handful, I would say 5 to 10 are going with C. Or rather with D, a few of them, but the large majority, and we have had a whole slew of answers come in. And folks, if you are able to change your settings to all panelists, everyone will be able to see your answers, but I can see them all. And so the large majority are saying C, a few D, 1 or 2 Bs as a possibility, but I would say the most folks on the line are thinking C. So Liz, how many types of minerals are there?
Hey, everybody is really smart. The answer is C. Nearly 6,000 mineral species are recognized by the International Mineralogical Association, which is the largest organization that supports mineral sciences across the globe. And what's really interesting about these minerals is most of them, over 80%, can actually form from interactions between rock and water. Okay, so now that you know what a mineral is, let's talk about how we identify them on Mars. There are a variety of techniques that we can use. One is we can study Martian meteorites. And so these are rocks from Mars that came to us after an asteroid or a big impactor hit the surface of Mars, flung rocks into space, and we here on Earth were just so lucky to intercept some of them. We also make orbital measurements or remote sensing measurements to identify and sometimes quantify minerals on the Martian surface. Some mineral bonds vibrate in the infrared wavelength region, and so we can identify some minerals on the Martian surface using infrared spectroscopy. And then we also use geochemical and mineralogical measurements by landers and rovers, and that's really what I'm going to focus on today. The Martian surface today is very cold, very dry. There is very little evidence, if any, for liquid water on the surface. Water today is locked up in the poles as ice or in mineral structures, but we do see a lot of geological evidence for abundant liquid water on the Martian surface, really 3 to 4 billion years ago. And so we see these sedimentary rocks across the globe that were deposited in lakes, rivers, and deltas, telling us that Mars had a lot of liquid water really 3 to 4 billion years ago. The minerals that we find in those sedimentary rocks can tell us a lot more information about what those past environments were like. This is a map of the Martian surface showing you some different types of minerals that have been identified from orbital infrared spectroscopy. All of these minerals are what we call secondary minerals, so they form from water-rock interactions, and again, tell us about the past conditions of the water from which they precipitated. So in blue are a type of mineral called phyllosilicates or clay minerals. These are dominated by minerals called smectite and chlorite. They typically need a lot of liquid water to form and a pH that's near neutral to basic. In yellow are chloride salts, so things like halite or table salt, and they are a marker of salty or saline fluids. Carbonates are in green. You'll notice that there aren't a lot of carbonates detected from orbit, and they form from evaporating waters that had dissolved carbonate within them, typically from communication with a CO2-rich atmosphere. And then in pink are hydrated magnesium sulfate salts. Again, they are a marker of more saline or salty fluids. In some cases, sulfates can be a marker of acid pHs. So across the Martian surface, there's been this sort of mineral stratigraphy that's been identified, where in some locations, the oldest rocks contain clay minerals, and then rocks that are on top of those, or slightly younger rocks, those contain sulfate salts. And so this observation led to a hypothesis that those rocks record a change in climate or environment over time, where Mars went from very wet with a neutral to alkaline pH to drier with salty acidic fluids. And so this hypothesis is a big reason why Curiosity landed in Gale Crater. Gale Crater is an impact basin. It's about 150 kilometers or 90 miles wide. What's special about Gale Crater, it has this a mound of layered sedimentary rock in the middle. It's about 5 kilometers or 3 miles tall. We call it Mount Sharp. And these lowermost layers of Mount Sharp vary in mineralogy and texture, suggesting that they may have recorded environmental changes that happened on Mars about 3.5 billion years ago. Okay, so zooming into these lowermost layers of Mount Sharp, some of these units are color-coded based on their mineral signatures from orbit. And so this brick red unit has a signature of the mineral hematite, which is an iron 3+ oxide. In green, this unit has a signature of smectite, so a type of clay mineral that can absorb water into its structure. And this yellow unit has a signature of hydrated magnesium sulfate salts. This white line, it represents Curiosity's traverse, and actually we are beyond this in the sulfate unit. And the goal of Curiosity was to study the mineralogy and the sedimentology of these rocks to determine what these ancient environments were like, how they changed over time, and if they would have been habitable to ancient microbial or microscopic life. Curiosity has a variety of science instruments, and so I'll introduce you to just some of them. Starting up at the mast, we have CheMin. CheMin gives us geochemical information using laser-induced breakdown spectroscopy. So basically, it fires a laser at a rock or a soil a few meters away, creates a plasma out of that rock or soil, and has a series of 3 spectrometers that read the plasma. Below CheMin, we have MassCam. It's a pair of cameras with 2 different focal lengths. MassCam gives us those outcrop to horizon scale images. Out on the arm, we have our sample handling system. This includes our drill, which we use to ingest powdered rock into CheMin, and our brush. We also have the MOLLE hand lens imager, or the Mars hand lens imager, or MOLLE, which gives us close-up views of rocks and soils with a resolution of about 20 microns per pixel. We also have the alpha particle X-ray spectrometer, or APXS, on the arm. That gives us bulk geochemistry of rocks and soils from up close. And then on the inside of the rover, we have 2 instrument suites. One is named Sample Analysis at Mars, or SAM. It's a thermal instrument and tells us about the volatiles in rocks and soils, including organic molecules. And then the instrument that I work on is called CheMin. It's an X-ray diffractometer, an X-ray fluorescence spectrometer that gives us quantitative mineralogy. Okay, here is a little movie to show you how CheMin works. So after we drill into a rock, we deliver about 20 milligrams-ish of powder to one of 27 reusable sample cells in a wheel configuration. During an analysis, we transmit an X-ray beam through the sample. Remember, we can't see X-rays with our eyes, but we've got our X-ray glasses on today. We have these piezoelectric actuators on the edges of the cells so that during an analysis, it shakes the cells so that the grains move convectively, and so that all different grain orientations come in contact with the beam. Those X-ray photons are diffracted from atomic planes in the crystal lattice, creating these, two-dimensional diffraction rings. Every mineral has a distinct X-ray diffraction, or a distinct set of rings, and so we can use these diffraction patterns to not only identify the types of minerals that are present in these rocks and soils, but also quantify them down to a detection limit of about 1%. Okay, I'm going to check in with you again. Another question: what types of minerals do you think CheMin found in Gale crater? And this time I wanted you to justify your answer. Is it A, clay minerals, B, sulfate salts, C, iron oxides, or D, all of the above? And just for reference, I put this map with the different mineral signatures from orbit behind you.
Great. So as you're giving some answers, justification is such an important part of science. And Prasad has said D, as water evaporated across different times and heights. Many folks are saying D right off the bat. Betty is mentioning that the mound had a lot of layers, so they're thinking D. Adrian is thinking all of the above, many different types of layers, and the different colors in the image represent some of those different minerals. Kevin is mentioning D because the rover went through all of those zones, but how do we know about those minerals? That's one of our aspects. JR is saying Gale crater has a record of early Mars and later Mars, or perhaps current Mars. We're having from Menominee High School, they're thinking D, since all types are seen and found and illustrated in that image. Jason is mentioning scattered surface layers and its different composites and layers. Randall Middle School says D, and do make sure you're putting your answers in the chat, not the Q&A. Steve from Wheat Ridge High School thinks D, the geology in the crater has changed over time. Skylar is mentioning Gale crater is said to be old, and they're thinking D, all of those assortment of minerals. Christy P and Alperin Y also say D. And actually, Jadell is mentioning a couple of minerals, phyllosilicates and sulfate minerals, perhaps taking from some of the information you may have shared earlier. So lots of D's out there. Liz, what do you say?
Oh, I love hearing all of your justifications. It shows that you are paying attention and digesting the information. That makes me feel good. I think you're going to have to keep listening to find out the answer. So let's keep going. Okay, so let's get into what we found with Curiosity and in particular CheMin. Here we are looking at a figure, so we're looking straight down at the crater. So the summit of Mount Sharp is just down and to the right here. This white line represents Curiosity's traverse over the course of the mission. And we have traversed over 34 kilometers in the last 12 plus years. We landed in August 2012. These different colors on the map represent different mineral signatures from orbital infrared spectroscopy. So the sort of mauve color is a signature of hydration or H2O or water in mineral structures, and the iron 3+ oxide hematite. In red, this is a signature of hematite at Vera Rubin Ridge. In blue, this is a signature of smectite. So again, that phyllosilicate or clay mineral that can suck water up into its structure at a location we called Glen Torridon. In green, this is a signature of hydrated magnesium sulfate salts, and this little sliver of yellow, it's sort of like a patchy distribution of clay and sulfate signatures. These white circles represent places where we have drilled into that rock and analyzed it with CheMin. Before I show you the CheMin results, I want to introduce you to some of the rocks that we have seen along the traverse. So you get a sense of these depositional environments in Gale crater about 3.5 billion years ago. So really close to our landing site, we found a conglomerate. And so a conglomerate is a type of sedimentary rock that has different sizes of grains, and the size and the roundedness of these grains in this rock indicate deposition in a river that was maybe up to 1 meter deep. Also close to our landing site, we stopped at a place that we named Yellowknife Bay. We found this fractured mudstone. Mudstone is another type of sedimentary rock made up of very fine grained materials, suggesting deposition in a really calm or quiet environment. And so this represents sediment deposition in a lake. Further along the plains, we stopped at a place that we named the Kimberley. It's made up of these sandstone beds that are dipping very gently towards the center of the crater. And this is a marker of a delta deposit. So this is where a river was flowing into a lake on the crater floor about 3.5 billion years ago. When we got to those lower slopes of Mount Sharp, we saw abundant laminated or layered mudstone. So again, a fine-grained sedimentary rock indicating deposition in a lake. Some of these laminations are thick, centimeter scale, suggesting deposition close to shore, but a lot of these are thinly laminated, millimeter scale, suggesting deposition far from the lake shore. We also see evidence for the drying of lake waters at some places along the traverse. This is a rock that we named Old Soaker, and if you look carefully on the surface, you can see these fossilized or preserved desiccation or mud cracks. So this is from the drying of muds around the margin of a lake in Gale crater about 3.5 billion years ago. When we got to this unit that has a strong signature of clay minerals from orbit, again, we saw more evidence for deposition in a lake, but we started to see some evidence for a change in the energy of the environment. This rock is a sandstone, and it shows these lines are tracing cross beds, so this indicates deposition from a river. In this clay sulfate transition area marked by this little yellow sliver here, we saw some evidence for really substantial or dramatic change in surface environments. This is a mass scan mosaic of that a portion of the clay sulfate transition. This light-toned bedrock has large-scale trough cross-bedding, and this is a marker of aeolian dunes, so wind-blown dunes, so dry, no water. These cross-beds are interspersed with these resistant lenses, and if we zoom into what those look like, you can see these symmetrical centimeter-scale ripple structures, and these formed from waves in shallow lakes between the dunes. And so these rocks mark a mostly dry environment, but with some wetness. Okay, moving on to the sulfate unit. Here we see evidence for mostly, almost exclusively, aeolian deposition or dry deposition. An example of this is this block here, which we drilled. You can see the cute little drill hole here. This is the Kanaima drill target. But you see these nice, straight, thin laminations. This pinstripe lamination is a marker of deposition in aeolian sand sheets. So again, no water necessary to form these rocks. Okay, checking in with you again. Another question for you. How did most of the rocks studied by Curiosity and Gale Crater form? And I want you to justify your answer. A, did they form from the cooling of lava? B, did they form from the deposition of sediments by wind and water? C, they formed from high temperatures and pressures deep in the Martian crust? Or D, they were brought to the Martian surface by an asteroid? What do you think?
Excellent. So as you put in those answers, again, that the justification is such a rich part of the answer. And Chris T is saying B, it was a lake, so deposition was likely the cause. We're getting a lot of other answers that are indicating B. Robert's mentioning B from water. Ella is mentioning B because they are mainly sedimentary rocks. Jadell is mentioning the deposition of sediment, so likely B. Adrian also says B, the layers suggest sediments. Heather is mentioning B because of the lamination. JR is saying sandstones, conglomerates, and mudstones are all sedimentary rocks. CheMin is mentioning that this region of Gale Crater, there's a lot of sedimentation, so B. Dalton mentions 3.5 billion years ago, we identified that there was flowing water shaping landforms, so B. Adam is also saying B due to the presence of lakes and rivers, perhaps from the past. Jason mentions B because it's dried out over time span, and that's where it came or is associated with past water flow. Let's see, we've got Menominee saying B, water movement was discussed and layering, and that's Menominee High School. Nick mentions B, the deposition of water down low and the deposition of wind up higher in elevations and those layered structures. Michelle V from St. Lawrence Middle School says B, evidence from weathering and depositing rocks from water and wind. Skylar is also adding B because we've already talked about the sediments and we know Mars has the history of water from the things you have mentioned. And Jaden says, I believe wind and water were common in the crater area, but so B, but he wonders, or this person also wonders about any possibilities of D. Randall Middle School also agrees B. So we've got a large majority of people who have been listening, Liz, and they have some justification in there. Overwhelmingly, they say D. What say you?
Oh, y'all are so smart. You guys have been listening. It was B. Almost all of the rocks that Curiosity has investigated were deposited by water and wind, and as many folks mentioned, these rocks are called sedimentary rocks. I want to call out somebody who wondered about the possibility of D. We do find some meteorites scattered across the surface, and so those were brought from, you know, a meteor, but the vast majority of the rocks that we investigate are sedimentary rocks. Good job, everybody. Okay, so based on those observations of the sedimentary rocks that we've seen as we've climbed Mount Sharp, we can create what's called a stratigraphic column. And so here's that stratigraphic column or stratigraphic section made up of all of those observations. On the y-axis, this is thickness of those different units, or in this case for Mars, it is just elevation. And we have driven through over 800 meters of vertical stratigraphy or elevation. These rectangles here show you the different rock types. So the longer the rectangle along the y-axis, it represents a larger grain size. There are also, you can also capture the different types of structures that are observed in these stratigraphic columns. And so looking at our stratigraphic column, the oldest rocks are at the bottom, the youngest rocks are at the top. So out on the plains, we saw those fluvial, deltaic, so deposited by rivers and deltas, grading into those lacustrine or deposited by lake mudstones, and then we moved into those aeolian rocks that we are in today. These black circles represent places where we have drilled into those rocks and analyzed that powder with CheMin. And so now I'll focus on what we've seen with CheMin. These bar charts represent the different minerals that we have identified with the CheMin instrument. So every color is a different mineral. This is a lot of information, and I don't expect you to digest it all. I will break it down into mineral group in just a little bit so we can talk in detail about these mineral types. But what I want you to appreciate is the variety of colors or the variety of minerals that we have identified with CheMin. Remember, there were only a few minerals identified from orbital spectroscopy. Here we see just dozens of minerals. And I want you to appreciate that the type of mineral or the colors changes within the stratigraphic section. So we have seen a change in mineralogy over time. So today I'll focus on the minerals that formed from liquid water. I'll focus on the clay minerals or phyllosilicates. We'll talk about the iron oxides and oxyhydroxides that we found, the types of salts, and we'll talk about what all of these minerals tell us about past environments in Gale crater. Starting with the clay minerals or the phyllosilicates in green, for all of these charts, I will list the largest amounts of each type of mineral so you get a sense for how much of each mineral is present. So for example, in this drill target AL, which stands for Aberlady, this rock had 34% weight clay mineral, so a third of it was made up of clays. Clay minerals are present in nearly all of the rocks that were deposited by rivers or lakes, and we don't see any phyllosilicates in those rocks that were deposited in dry aeolian conditions. And this is consistent with what we see from orbit. The peaks in our XRD or X-ray diffraction data from CheMin help us identify the types of clay minerals that are present. And based on our interpretations of those patterns, most of these clay-bearing minerals contain smectite. So again, that's a type of clay mineral that can absorb H2O or water in its structure. Though we do see some important variations throughout the stratigraphic section that can tell us more about these past environments. Some of these drill holes have clay minerals that formed at relatively slightly warmer temperatures. So we're talking like 50 to 100 degrees C, so less than the boiling point of liquid water on Earth. So suggesting that there were some warm fluids moving through the crater. And some drill holes have clay minerals that were modified or changed after they were deposited. So they would have formed in these lake waters, those sediments would have been buried, and then those clay minerals that were originally deposited were changed a little bit, telling us that there were groundwaters moving through here even after those lake waters were gone. Okay, moving on to the iron oxides and oxyhydroxides. Hematite is in red, it's an iron 3+ oxide mineral. Magnetite is in black, it's an iron 3+ and iron 2+ bearing oxide mineral. In brown is octagonite, it's an iron 3+ oxyhydroxide with chlorine in its structure, and in orange is goethite, which is an iron 3+ oxyhydroxide. Hematite is the most common secondary iron-bearing mineral that we see in Gale crater. It forms under oxic conditions, and so it is a measure of oxic conditions. Magnetite in black is most abundant at the base of the section or in the oldest rocks. Since it has some iron 2+ in its structure or reduced iron, it forms in less oxic or more reducing conditions than hematite does. So we see variability in redox conditions in these waters throughout Gale crater. Octagonite in brown formed from acidic and salty fluids. We see it sort of peppered throughout the section, and so it tells us that there were sometimes acidic and saline fluids interacting with these rocks or sediments. Goethite in orange is discovered in these aeolian units along with hematite. And if we assume that they precipitated together, we can use the ratio of hematite to goethite to constrain the pH of those conditions. And these ratios are consistent with a near neutral pH, so not basic, not acidic. And we see some interesting variations in the size of the crystals of the hematite within the stratigraphy that tell us more about how that hematite formed in some places. This is a mass scan mosaic of that Vera-Rubin ridge, so that feature that had a strong signature of hematite from orbit. You can see different colors, red, orange, gray, purple. We drilled and analyzed one of those red rocks. This is the Stower drill hole. For scale, the diameter is about 1.5 centimeters, or the size of a US dime, and we drilled down just 3, 4, maybe 5 centimeters. This drill hole had the most hematite of any drill target to date, so not surprising because we detected hematite from orbit. We also drilled into one of those gray rocks and found that it also has abundant hematite. What's important about gray hematite on Earth is that it commonly forms in relatively warm water, so like 100 to 200 degrees C. And so again, this is a marker of some warm waters moving through Gale crater, probably groundwater. Okay, ending with salts. Calcium sulfate is in this light yellow color. We see all 3 varieties of calcium sulfate: anhydrite, basanite, and gypsum. And we see it in the sedimentary matrix and in veins, telling us that it precipitated early during the lithification process and late after the rocks had already formed. Jarosite is in pink. It's an iron 3+ sulfate, and it forms in acidic fluid. So like octagonite, its presence in some locations tells us that there were some acidic fluids moving through these rocks. Starkeyite and kieserite are these hydrated magnesium sulfate salts in purple. We found them in the sulfate unit, so not a big surprise that we would find those in the location where we identified the hydrated sulfates from orbit. What was a surprise is this bright blue bar. This is iron 2+ carbonate. It is called siderite. It's a mineral siderite in most locations. We did not expect to find siderite from orbit, even though it does have strong bond vibrations in the infrared. And so we think that because it is with hydrated magnesium sulfate, we think that the bands from hydrated magnesium sulfate are actually masking or preventing the detection of carbonates in these units. We think it formed from dissolved bicarbonate and carbonate-bearing solutions at neutral to basic pH. And if similar amounts of carbonates are found in those sulfate-bearing rocks across Mars, they could account for tens of millibars of sequestered CO2. And so this is really important for understanding the composition and the thickness of the ancient Martian atmosphere. So we have seen mineralogical evidence for important changes in these environments over time. We see evidence for less surface and groundwater over time because we see those clay minerals which require a lot of liquid water. We find them in those rocks that were deposited by rivers and lakes, but they are absent in the rocks that were deposited under dry conditions. We think that those surface and groundwaters became saltier or more saline over time because we see those magnesium sulfate salts of section. And we see some evidence that some of these groundwaters were warm and or acidic, but not everywhere, not pervasively. Okay, so another question for you just to check in. Which type of mineral found in Gale Crater is the most interesting or intriguing to you, and why? A, clay minerals, B, sulfate salts, or C, iron oxides? I'm really looking forward to your answers.
Yeah, me too. This should be really interesting to see what folks have to say. Liz gave you a lot of the pieces of the story from these minerals. So what are most intriguing or interesting or lead you to the most number of questions, and why? What about that makes it interesting or intriguing to you? So Scott is mentioning C, could be used to perhaps build things. Adrian says B, sulfate salts. I wonder if there was life in salty waters long ago. JR says sulfate salts because they were intrigued by the blueberries. Greg mentions mascalite is a glass that forms when a meteorite blasts rock off the surface of Mars. So perhaps that is something of interest. Nick says clay minerals could hold clues to ancient biology if it ever existed. Tomball High School says B because they know least about them and want to understand them better. Let's see. Adam mentions B, sulfate salts, because sulfates have unique chemical compositions that reflect the environment and its history. Let's see. University of Puget Sound, this individual saying iron oxides and their role in determining pH. St. Lawrence Middle says A, clay for carbon-based life. Saluni says, for this individual, iron oxides, because the formation of iron oxides gives a sense that there was a trace amount of O2 present in the Martian atmosphere. Dolores says B because of the involvement in the development of life. Skylar mentions B, sulfate salts are the most intriguing because looking at the different amounts on the layers can perhaps give an idea of what Mars may have been like, and gives more questions like, why did the amount of it increase and then why did it disappear? Jadel says jarosites are of interest. Betty mentions C, what turns the color of the surface red. Ella mentions A because water may suggest life and is completely different than the Mars we know today. We've got some really, really amazing answers. Oh, and Cypress High School, let's see, they mentioned that, that they're going to have to go, but their students say B and C, that they are very interested in. Good luck on your finals for those of you there in Cypress Park High School. So we've got some really interesting things that are intriguing folks out there. What do you think, Liz?
Oh my gosh. Well, I loved hearing all of those answers, and it sounds like we've got a lot of budding or amateur mineralogists out there. Of course, there's no right answer. All minerals are equally great. As a lot of you noted, these are all interesting minerals because they form by reactions between water and rock. If I had to choose one that I like the most, I would say clay minerals are especially interesting to me just because I studied them intensely in school. Okay, just to start focusing on the future of planetary mineralogy, There is another active Mars rover today called Perseverance. Perseverance is in Jezero crater. This is an orbital image showing you the western edge of Jezero crater, so you can see the crater rim here, and you can see a channel that goes into the crater and a delta. So this is another place on Mars where a river flowed into a lake on the crater floor. So that is one main reason Perseverance went to study this feature and this location. In addition to Perseverance, a helicopter named Ingenuity tagged along. And so this was just a really successful technology demonstration in terms of the future of planetary mineralogy. I can imagine sticking like a spectrometer onto one of these things and finding out the mineralogy through some local remote sensing. But in terms of the future of planetary mineralogy for Perseverance in particular, Perseverance is in Jezero collecting these sort of pencil-sized rock cores and sediment cores for the hopeful eventual return to Earth, so that we can study these samples in our instruments here in our laboratory, which can do more detailed mineralogical analyses than our instruments on the rovers. Minerals are also a key to planetary exploration, especially by humans. So, for example, minerals have H2O, volatiles, and metals in their mineral structures that we can use in human exploration. H2O, or water, obviously, can be used for drinking or for rocket fuel. Rocks and minerals may also be used for constructing habitats for humans. So, for example, lunar soil or regolith may be turned into bricks for constructing a habitat. And instruments like CheMin will be important for characterizing those construction materials. Thinking about the future of planetary mineralogy, of course, return samples not only from Mars, but from the Moon and a variety of other planetary bodies will be really important for interpreting the geologic history of those solar system bodies. Minerals are going to be important resources for humans as we travel to the Moon and to Mars. And I personally am working on developing new X-ray diffractometer instruments to send to other planetary bodies like the Moon, Venus, and Mercury to get some quantitative mineralogical information from those planetary surfaces. And so with that, I thank you for your attention.
Awesome. Liz, that was so fabulous. And I hope everybody out there had an opportunity to think, reflect, and learn something, because I know I learned so much from Liz, and the future is exciting for planetary exploration and the connection to what minerals have to tell in terms of the story. So fabulous presentation, Liz. Thank you so much for making it in such a way that everyone could understand different portions and be able to attach their own knowledge to some of what you shared with us today. So fabulous, fabulous presentation. But now it's time for some Q&A. And we're going to see what participants have in terms of any questions. Now, for those of you on the line, please put any questions you might have in that Q&A area so that we can find your questions and be able to answer or ask Liz to answer those questions. Now, some of you did actually put in some questions in your webinar registration. And so I'm going to start with some questions that have already come in while folks think about any questions that they do have or any additional questions. Now, I will note that we are about 5 minutes to the top of the hour, but Liz has graciously agreed to stay on the line for a little bit of extra time so that we can get to as many questions as we possibly can. So put those questions in the Q&A, and I'm going to start with some pre-webinar questions. And actually, my first question comes from a group at Katy High School here in Texas. And they're wondering, can you please describe the potential for Martian mineral resource extraction and what that could mean for future careers in planetary geology?
Yeah, that is such a good question from Katy High School about using martian minerals as resources. As you saw in Gale Crater, there are lots of H2O, OH, so water-bearing minerals. And so I think the greatest resource for humans will be that water in those mineral structures. And so some of the water is more available than others depending on the mineral. So some minerals like to give up their water more easily. So if you heat them, the water will come off at lower temperatures. So things like these hydrated sulfate salts, I think you probably get the biggest bang for your buck in terms of water. So that's what I would target for humans going to Mars in terms of mineral resources.
Yeah, and I certainly do think that there are some future mineralogists out there, folks that are going to be perhaps studying Mars. Doesn't matter your age right now, the future is open for you to perhaps pursue that future career. So thank you for your first answer to that question. I have another one that is interesting. This comes from Skylar in Florida, and they are wondering, could we find traces of bacteria where water used to be present? Could this clue us in on what sort of life perhaps existed?
Oh, Skylar, that is like what has driven like the Mars exploration program for like the last 30 years is, was there life there? And you hit it on the head. We are targeting these sites with multiple lines of evidence for liquid water, morphological evidence for lakes and rivers, and also mineralogical evidence telling us that there was, maybe clement conditions in the ancient Martian past. With the instruments that we have on Curiosity, we cannot positively identify microbial life. We don't have instruments to detect that. With Perseverance, they're getting a little closer to being able to detect sort of macroscopic expressions of life. So, microbial mats, that sort of thing, or stromatolites, if you're familiar with those. But that really drives home the importance of bringing samples from Mars to Earth so that we can use our high-powered instruments in our laboratory to look for evidence of microbial life. So thanks for that question, Skylar.
Yes, excellent question, Skylar. Here's a question from Ken B., one of our solar system ambassadors in North Carolina. Ken is wondering, any fluorescent minerals found on Mars, and is fluorescence a potential marker for organics?
Oh, that is a great question, Ken. And we do have on the Molly camera, which is on the arm, it has different lights on it of different wavelengths. And so it does have a UV light so that we can look for any minerals or phases that might fluoresce in the ultraviolet wavelength range. And so far, we haven't seen evidence for that. And I mean, I know that extant life on Earth can fluoresce, but I don't know if there was, ancient stuff that was dead for 3 billion years, if it would still fluoresce. But yeah, great question.
Excellent and very, very interesting. And here's another one of our solar system ambassadors from Indiana, Adrian, and she's wondering, let's see, I just lost her question. With regards to here it is. It's somewhat related to water and this idea of water. How deep below the surface might there be liquid water? And are there any plans for underground rovers or rovers that can sort of peer into the underground to see any detection of water?
Oh gosh, that's such a good question. Who asked that one again?
That was Adrian, one of our solar system ambassadors from New York.
Okay, cool. Yeah, great question, Adrian. And we have radar observations from orbit that can sort of like see water in the subsurface or see evidence for water in the subsurface. And there is some data that suggests that there are subsurface lakes around the South Pole that are like maybe 1.5 kilometers or like a mile below the surface, which is just amazing to think about what are the conditions in those lakes? You know, could life be living in the subsurface of Mars today? There are no plans to drill into those or to explore them any further. But I love the way you're thinking. Maybe we should design a mission for that.
Designing a mission sounds like a plan, you know, and for folks out there, there's always ideas of designing new missions to be able to answer new and interesting questions. So, you know, people propose different missions, whether it's to Mars or Venus or the moon or whatever. And so, you know, all ideas are good ideas. And by the way, that was Adrian, our solar system ambassador from Indiana. We have a different solar system ambassador from New York, Tish, who is wondering about if you can compare some of the Mars mineral content to what we see on the moon.
Oh, yeah. Good question, Tish. Yeah, so they're two totally different bodies. What is really important about the mineral assemblages that we find on Mars is that aqueous history. So remember at the top of my presentation, I talked about how most minerals on Earth can form from water-rock interactions. Well, we know that the moon has some ice at the poles, some water ice at the poles, but it didn't have this long history of liquid water that could form different minerals like clays, like iron oxides, like sulfates. And so the variety of Martian minerals or the variety of minerals on Mars will inherently be greater because of this history of liquid water. The moon does have different processes acting on its surface, like space weathering from high energy particles coming in from space. There's no atmosphere on the moon, so no way to protect it. Mars has a thin atmosphere to protect it from some radiation. And so there will be these space weathering reactions that happen on the very outside of the lunar regolith that will create different minerals and glasses. So some differences.
Awesome. Thank you so much for that. And, you know, the moon and Mars and all these other worlds, there's similarities, there's differences, but they all piece together a different part of our solar system's history. So here's a question from both Dolores as well as Caesar. They're wondering about, you know, future samples. And let's see where that question went. Future samples and the state of proposed possibility of samples coming back to Earth from Mars.
Okay, so like the status of bringing samples back from Mars.
Correct.
Yeah, it's a great question, and it's been really a hot topic in the news because we really across the world we scientists, planetary scientists, have been working towards Mars sample return, specifically with the samples that Perseverance is collecting. And recently, I mean, the budget is trying to be, is being figured out right now at NASA, but if we're reading the writing on the wall, it looks like Mars sample return will be put on hold for now, and with the possibility of humans bringing samples back. So it means that bringing samples back from Mars is still a high priority, but we don't yet know how and where we will get samples from.
And the interesting part of this is we actually do have samples from Mars in meteorites. And so there are Martian meteorites that have been collected in different parts of the world, and those meteorites themselves do tell a story. We don't know the context from where they came to help build and piece together that story, but there are some pieces of Mars that actually have made their way to Earth. through just sort of orbital dynamics, I perhaps can say. So
Yeah.
every sample has a story to tell. Rocks are such a powerful, powerful storyteller. So I have another question for you. Let's see, Nick. Nick is wondering the current determination, or what is the current determination of when Mars went from warm and wet to cold and dry, and how quickly might it have transformed? Any thoughts on
Oh my
that?
gosh. Oh, well, that is a great question, and one that I and many of my colleagues are trying to answer. And that's really one main reason why Curiosity went to Gale Crater, is to try to figure out when and how the Martian surface dried out. With Curiosity, gosh, we are learning so much about the ancient history of water on Mars. We are learning that, yes, we see evidence for those surface waters drying out over time. You know, we saw that transition from the lake deposits to the river deposits and the aeolian deposits. But we're seeing some really interesting information data with CheMin. We recently drilled into a fairly young channel, and I cannot put a date on how young this is, but representing some of the last gasps of liquid water in the crater. That channel brought rocks down from higher in Mount Sharp, so in younger rocks that we have yet to visit, and we find clay minerals in those rocks. So it suggests that there is another wetter interval that's younger than where we are today. So I think this drying out of Mars was not continuous. It was probably episodic and moved back and forth between drier and wetter conditions over time. And it probably changed where you were on Mars. I don't think it was a global phenomenon. And so I think what we'll find, and what we are finding with Jezero, is telling a slightly different story of water there. Another thing that we see with Curiosity is evidence for fairly young groundwater. So these sediments were deposited in lakes and rivers and by the wind about 3.5 billion years ago. The SAM instrument, that thermal instrument, performed potassium-argon age dating on some jarosite in one drill hole from a lacustrine or lake mudstone, and showed that jarosite is only 2 billion years old. Okay, so that's still pretty old, but it is 1.5 billion years younger than the age of the lakes that deposited those sediments. And so it means that there was a long history of water either on the surface or subsurface of Gale Crater.
Fascinating. And it's amazing, this question of warm and wet, cold and dry has been out there for so long. And it's almost as though the more we learn, the more questions we think to ask, and perhaps even the more evolved we come in the types of missions or instruments that we may want to send to Mars in the future. So a few more questions, Liz, if you still have some time. Okay.
Totally.
So JR from Norwalk State Community College is wondering, in terms of oxygen, where did the oxygen on Mars come from? Was it atmospheric? Is there still oxygen out there? Can you talk a little bit to that?
Yeah, that's a great question, JR. And in the distant past, we don't totally know. It certainly could have been atmospheric, but there is a way to create oxygen, especially in surface waters, through photo-oxidation reactions. So those oxic environments could have been from photo-oxidation reactions in the water column caused by, ultraviolet and higher energy particles coming in and interacting with the waters.
Excellent. Well, speaking of instruments, and we were just talking about, future missions and perhaps instruments to send, Jadel has asked, what type of instruments are you implementing perhaps for future missions?
Ooh, good question, Jadel. So I personally am making improvements with some of my colleagues to the CheMin instrument to hopefully fly it on another mission to Mars or missions to the Moon, Venus, Mercury. The improvements that we're making to that mineralogical instrument are to basically make it faster and to make it use less power. So we're using different detectors that don't require cooling, so it uses less power, so that there can be other power for other instruments. It makes it more accommodatable on different missions. And then we're also figuring out ways to make it a lot faster. So again, using less power and requiring less time on a mission, making it more attractive to missions. So for CheMin today on Mars, we analyze a rock powder anywhere from like 8 to like 22 hours total. So that's a pretty long time. But with this new and improved CheMin, we could get the same mineralogical information in just like 5 minutes.
Wow, that's 5 minutes sounds so quick.
A lot less, yeah.
Well, here's a question from Jaden. Jaden is wondering, what was your favorite project that you've worked on throughout your career?
Oh, that's such a good question, Jaden. I have been lucky to work on amazing projects with amazing people. But my favorite certainly is working on the Curiosity rover and with the CheMin team. It has, gosh, I mean, coming from a background of mineralogy, clay mineralogy, and XRD, and getting to do XRD on Mars, looking at clay minerals on Mars is just so awesome. And it really, probably more is about the people that I work with. Everyone is just so generous with their time. They are interested, they are smart, they are kind, and I really sort of grew up in my career on the Curiosity team and have had some really great mentors and friends throughout that part of my career.
And I totally agree. The people and the science and the planetary science community overall within the Science Mission Directorate, and beyond, it's an amazing community of like-minded people that are all working together to sort of better understand questions that people have been asking for so long. And so, Liz, how long have you been working on the Curiosity mission?
So I started in 2011, right when it launched. So that's, gosh, 14 years.
And what is your do you have a particular role with the CheMin instrument?
I do. I'm the deputy principal investigator, so I'm like sort of second in charge.
And is there a laboratory at the Johnson Space Center where you're able to sort of do some work that's not on Mars, but associated with the work that you're doing on Mars?
Oh, yeah, definitely. There are a variety of laboratories here at the Johnson Space Center where we can analyze, like the analog materials that we collect in Iceland or Oregon or wherever. We also synthesize or we make minerals for comparison to what we're getting back from CheMin and with Curiosity. And so in our laboratory, we have different types of X-ray diffractometers. We have, the high-end, high precision, high resolution instruments that are, like the size of a refrigerator or 2 refrigerators. And then we have analog instrument for CheMin. So we have this sort of like tiny microwave size instrument that we can collect data that are directly comparable to the data that we get with CheMin.
And future careers, we're always looking to think about, expanding the community and having new folks join the team. So I'll come back to that question. I'll have 2 more questions if that works for you. One of them is, is from Alperin, who actually from Layla, who is wondering, is physics at all a part of the work either that you do or that's involved in the work associated with exploring Mars?
Oh, totally. I mean, there is physics deeply involved in like X-ray diffraction and all of these mineralogical and geochemical techniques that we use on the surface. There are physics involved with, you know, like the atmospheric interactions. I mean, physics is like the basis of everything, and I always wish that I took more physics. That leads to a larger comment that there are a variety of things that you can study or do and become a planetary scientist. So not just geology, mineralogy, geochemistry. You can be a physicist, you can be a chemist, you can be, gosh, I mean, you can be a biologist. And it's also not just science. I mean, there are artists who are involved in, who work at NASA. There are lawyers that work at NASA. So whatever your interest is, if you are passionate about space exploration, you know, NASA's got a spot for you.
Great. And I might have fibbed a little bit. I have maybe three more questions, if that would work.
Great.
Okay.
Totally.
So we had a question that came in from Aditum that is asking, how reliable are Earth analogs, and where do you get some of those Earth analog samples from for simulating Martian conditions?
Oh, that's such a good question. And there is no perfect analog, but it also, you know, it depends on what you are studying. And so there can be, you know, physical analogs, or you can go to, you can collect fluvial or, you know, sedimentary rocks that are deposited in rivers that have, you know, the right grain size and the right structure, but maybe not the right mineralogy. Or you can go to places like Iceland, which have the right mineralogy for Mars and the moon, but maybe they had too much water, or pretty much everywhere on Earth has too much life for Mars. And so life, organics, they can definitely change the mineralogy and geochemistry in ways that we wish they wouldn't for studying Mars. But hey, like I said, there's no perfect analog. So that said, Iceland, Hawaii have the right rock types for studying things like Mars and the moon. Antarctica and the Atacama have sort of like the right environments, very dry, in some cases very cold. So like I said, it sort of depends on what you're studying. That will guide where you should go.
Excellent. And do you have a favorite place to go pick up analog rocks or to explore?
Oh my gosh, I love Iceland. I mean, coming from like Southeast Texas, where right now it's like 10 million degrees outside, being in Iceland is just like, it's so beautiful. There's very little vegetation, so it actually like feels like you could be on Mars, you know, 3 billion years ago.
Very interesting. So here's another question related to the names of regions and rocks. You mentioned so many different names of places, Glen Torridon, Bradbury Landing Site, which may not have been mentioned, but someone talked about it in the chat. How Old Soaker, how did some of these names come to be?
Yeah, it's such a good question, and these are all informal names, but the team selects, you know, we map out quadrangles, and we name those quadrangles after a well-known area on Earth, or an area on Earth that's well-known for its geology. And then we identify names associated with that place, and it's typically, you know, like towns or mountains or other geologic features or rivers or whatever. So let me see if I can think of a good example. Right now we're in the Altadena quad. So Altadena is the city where the Jet Propulsion Laboratory is in, which is where the mission is run out of. And so we have names like Arroyo Seco, which is the arroyo behind JPL, and other features and towns close by. And so that's how we get our names. And then whoever's working operations that day when we're selecting targets or places to collect data, those people who are working that day just look at the list of names, and then they pick a name from the list to name those different targets.
That's so very interesting. And one of our solar system ambassadors from Indiana had mentioned that the Bradbury landing, perhaps you can confirm this, was perhaps named in memory of the author Ray Bradbury, who died in 2012 before Curiosity landed. And so Ray Bradbury was the author of the Martian Chronicles. And so that's a neat tribute as well.
Yeah, we typically don't do like names for tributes, but occasionally, rarely, for really great people, we will name targets or features after them.
Excellent. And perhaps, that was something that someone had added into the chat, whether that's official or there's some other reasoning behind that name. But it is great to think about, there's great books out there about Mars, and perhaps the Martian Chronicles might be one of interest to folks. Well, my one last question, and Sakshi, and please forgive my pronunciation if I am incorrect on that, and others are wondering, what advice would you give to folks who are willing to study deep into these types of topics and preparing for their future careers, perhaps in planetary science? What advice would you have for folks?
Oh gosh, my advice is really to follow what you're passionate about. So follow your interests. Get involved with as many projects as you can. Don't be afraid to collaborate with folks. Don't be worried about things that you don't know, because there are people out there who can fill in those gaps for you. Focus on the things that you like and what you do know. If you're in undergraduate school, I would say get involved in research that you're interested in. That'll help introduce you to people who are involved in planetary science or whatever you're interested in doing. There's probably more advice. I would say be active. Say yes a lot.
Yes. Okay. So Paige said in the chat, sorry for the technical difficulties. And then we'll go ahead and bring the webinar to a close. So thank you so much, Liz, for your talk. That was awesome. I learned a lot, and I know our participants did as well. So thank you everyone for joining us today. Thank you, Sarah, for helping answering the questions in the Q&A. And again, thank you, Liz. It was a wonderful, wonderful webinar.
Yeah, you're welcome. And thanks everybody for the good questions and for, staying engaged and interested. So bye, everybody.